In sac208 number 2, we've got a capacitor that's got a mica dielectric. Alright, somebody connects a power supply across the terminals of the capacitor, sets the voltage to 115 volts, and then disconnects the power supply. So we get some charge on the capacitor and a voltage across it of 115 volts. Then, without connecting it to anything else, they slide the dielectric, the mica, out, and we get a new voltage, but there can be no charge. Check out the capacitor. We'll draw a before and after picture. Here's the before picture. The capacitor is charged up. It's got some mica in it. So in this before picture, it's already been connected across the power supply so that the voltage is 115 volts, and the power supply has been disconnected. That's our before situation. The capacitor has some charge on it. It's got value of electric potential difference between the terminals of 115 volts. We'll call the capacitance of the capacitor with that mica dielectric in there capital C, and the charge we'll call Q. Keep in mind, when we slip that out, the charge can't change. There's no way for the charge to get from one side to the other. It says it's isolated from the surroundings, so the charge in our after picture is going to be the same. So the only difference really in the case of the after picture is that instead of mica for the dielectric, we've got air. Got the same amount of charge. No place for it to go. I'll call the amount of charge on there capital Q. As before, use the same symbol since it's the same amount. Call the capacitance C prime. That does change because the capacitance depends on the dielectric that's in there. And furthermore, if I change C, keeping Q the same, then V has to change so that that product CV is still the same. So for instance, if C decreases, then V has to increase in order to make it so that the product stays the same value of Q. And the Q stays the same. The amount of charge on the capacitor stays the same because there's no place for it to go. So we will have a new voltage, call it V prime, and indeed that's what we're looking for, the new potential difference between the plates of the capacitor. Let's try starting with our equation for capacitance. The Q is equal to CV. I'll write that down once for the before picture. That's the defining equation for the capacitance. And write it again in the case of the after picture, recognizing that I've got the same Q but a different C and a different V. So I'll call it C prime and V, but use the same symbol, Q, for the charge. Now, the left-hand sides are identical, so the right-hand sides must be equal to each other, so I can set CV equal to C prime V prime. We're looking for V prime, so let's just go ahead and solve for V prime. See where we are. I'll be dividing both sides by C prime and then switching sides. I get this equation. V is known, 115 volts, but neither C nor C prime is known. All we really need is the ratio, but we don't have enough information even to get just the ratio, C to C prime. We do recognize that the capacitance depends on the dielectric that's in between the plates, besides the geometric factors. And we've got two different values of dielectric constant. And that's what makes it so that we've got two different values of C. The capacitance in terms of the physical characteristics of the capacitor is given as the product of the dielectric constant with the electric permittivity of free space and the ratio of the area of the plate of either capacitor, the plate area, to the separation. So over in the after picture, we've got a different capacitance, really just because dielectric constant is different. We'll call the dielectric constant in the after picture K prime, and over here in the before picture I'll call that K. So K is the dielectric constant for mica, and that's given as 7.00. It's got no units. And the dielectric constant for air, or vacuum if you wish, depending on where the capacitor is 1.00. So the capacitance in the after picture, same as the before picture, except a different value of dielectric constant, the 1 instead of the 7. I'll call it K prime instead of K. Now these two equations, if you look at them, essentially identical, except I got, in the second one, I got K prime instead of the K. Easy way to make it so that all these things that are common, the epsilon 0, the A, and the D, cancel out, is to find the ratio of one to the other. And indeed, that's what I need. If you look up above, we need the ratio of C prime to C. So let's go ahead and calculate that using the properties of the capacitor. It's just K epsilon 0 times A over D for the capacitance in the before picture. And then I divide that by K prime times epsilon 0 times A over D, the after picture. We see the epsilons cancel out and the A over D's cancel out, and our C over C prime is just K over K prime, the ratio of the dielectric constants. So we'll go ahead and copy that equation down with C over C prime expressed as K over K prime substituted in for the C over C prime that appears above, and I get that V prime is K over K prime times V. And K is given as 7.00. K prime is, we know is 1.00, the dielectric constant for air or vacuum, and we got to multiply that times 115 volts. And that yields 805 volts. And that's our answer for SAC 208.